Yeah. Test, test. Roman, Ian, can you all hear me, see my screen?
Yes, sir.
Okay. Hey, everyone, did I send out I can't remember, did I send out an email with a link to the folder where I'm putting the notes now? Okay, I just want to make sure. I know I did the folder, I know I uploaded the notes. I don't remember if I sent the email. Okay, one more minute. All right, it's 9 o'clock. How y'all doing? Wednesday. All right, so a couple of administrative things first. I've been thinking a lot about the next exam, which is, let's see, where's that schedule? There we go. Next exam is supposed to be November 10th, which is what, is that 2 weeks? 2 weeks. And that is the day I told you I'm going to be out of town. Did I mention that? My wife's going to have surgery in Houston. Yeah, so I'm going to be out of town. Here's what I'm thinking about doing. I'm thinking about making exam 3 a take-home exam. So it would be over you know, pretty much everything up through whatever we get through next week. And so whatever we finish with on the 3rd, a week from today, that would be on the exam. Anything we do on Monday, the 8th, we would not have on that exam, but it would be take home. Now, that means it would be harder than an in-class and longer than an in-class, but it would be take home. So what do y'all think? What's your initial thought? Would you prefer a take home, or would you prefer to do an in-class? Or do you need time to think about it?
Take home sounds amazing.
I don't mind if we start at the
Yeah. Okay. It's really not because I'm not going to be here, because I can always get a sub to come in here and just sit down and give a test, but it's more because the material, it's a lot of material. So I want to give you time to work it out. So you know how we've been doing like areas between curves and then rotating them, and we did arc length last time, surface area. And I told you on the exams, I'm just going to have you set up the integrals. That will still be the same for most of the problems. It'll be set up. It's just going to be more complicated regions. You know, it's not going to be like x squared, you know, in some line. It's going to be something complicated where you're going to probably need some graphing utility to get your regions, you know, so it'll be a little more involved, but you'll be at home and you'll have your own resources to do that. So let's tentatively plan for that, a take-home exam for exam 3, okay? All right. So we are going to start chapter 8 today, but I wanted to mention to you that in our book, there is another section in chapter 7 called 7.6, and it's called Applications of Integration. So what we've been doing is, everything we've been doing is very geometric, very visual, but there are obviously other applications to integration that we are not going to cover in this class because, well, this is a math class. It's not an applications of this math class. So there's all sorts of applications you can do. And this is, if you're an engineer, this is where, when you get to an engineering course, you're going to do the applications. You just need to make sure you know how to do the integration. So I wanted to just briefly show you one quick application. We're not even going to do any examples. And that is the concept of work. So if you were in if you take a physics class, right, then, so this section has examples like applications like work, hydrostatic pressure, centers of mass, moments of inertia, things like that. All of these different ideas are tied into the integral. So I'm just looking at one of those. Right? We just don't have time. I wish we did have another 3 weeks. We could get into this pretty deep. So the idea of work in a physics class, again, I'm not here to teach the physics, all right? It's, you know, you learn about this thing called work and force and mass and acceleration and blah, blah, blah. And you get to a final formula for the work done moving an object in a straight line. So if let's say I put a book on, set my book, let's say my backpack on the table or on the floor, and I start dragging it along the floor in a straight line, then the work that I do is the force that I apply to the book bag, times the distance that I pull it through. Okay, that's in physics, that's the definition of work. Well, that's easy if your work is constant. So if I grab a backpack and I just start dragging with the same force the whole time, then that force is constant. I just multiply that force times the distance and I've got my work. All right. Visually, this is what that would look like. Here we go. Oh, these windows hide from me here. Here we go. So here is a visualization of that idea. So what I have here is my backpack, okay? And the arrow represents the force I'm applying to it in that direction. So the length of the arrow represents the force. If I increase the force, right, then the arrow gets longer, all right? So now I'm going to start dragging this thing across the floor. When I drag it across the floor, I have the computer. It is, let me take the force back to 2. So my force is 2 whatever, okay? Don't worry about that. And then I just need to multiply by the distance. So right now I've gone 6, whatever, feet, meters, whatever it is. So I multiply the 2 times the 6. I mean, yeah, times 6 and I get 12, right? Pretty straightforward stuff here, right? But I want you to imagine that force a different way, even though I'm pulling the force in that direction, right? Think about if we were to try and visualize that force somewhere in this picture. So what I'm going to do is I'm going to have you look at every point along this path. I'm going to measure the force, which is 2, and I'm going to put just a dot above it. So it'll look like this. So I'm pulling this direction. This point has traveled the red distance, right? And the 2 right here is my force. If I increase my force, then it increases that area above it, right? So the computation of the work, right? Like here I'm getting 45, right? Is the work done? It is, yes, 3 times 15, but it's also the area of this rectangle, right? 15 times 3. I wanted the force to be 2, sorry. Okay, so 2 times 15, that's 30, right? That's a constant force. What if your force was variable? In other words, you're pulling and then not as much force and then maybe a little bit more force, right? Back. So if your force is not constant, how can we find the work? Well, if we do the same thing and we say, okay, at each point, let me just represent the force at each point, then what you get above it would be non-linear, right? It would be something. And then if you could find the area between that line and that curve, then that would be your work. Does that make sense? And that's exactly what we do in physics. So look at this picture I have here. Take this one back. So I want you to notice right now the force is, all right, now the force is 2, right? Or 3, sorry. And just watch what happens when I move this across. The force is not going to stay constant. Watch. See it change? It got bigger and now it's getting smaller and then bigger and then now smaller. See the arrows getting bigger and smaller? So if I were to try and at each point, look at the force at each point, then I would have this, right? It's variable. So when I get to moving it from 0 to 15, if I want to know total work, then I need the area underneath this curve, integral, right? So again, it's all about, with this idea of work, it's all about, do you have a constant force? If you do, simple math, you don't need a calculus. But if you have a non-constant force, then you need integration so you can find areas. And this will work. I said I wouldn't show you another example. We're not going to do any computations here, but another example is if you wanted to have, let's say you have this funnel, right, and it's full of water, and you need to pump the water out of here, right? You need to pump it out. The question would be, how much work has to be done to move all that water out of the funnel? So the way we do that is we imagine that we take the volume of water here, and what we do is we cut it into an infinitesimal little slice like this, right? Like that red slice. And we can find the volume of that. And if we know the density of the water, we can find the mass. And if we know the mass and the force, the mass, if we know the mass and force, we can find the acceleration. You have to, force equals ma. So there's, basically we have a mass, right? And we want to move that mass through a distance, right? Through a distance to move it up and out. So we move this thing up and we move it. We don't move it. Whoa, what's going on? Uh-oh. Not sure what happened there. There we go. We have to move that up, right? This goes in, we take any piece here, and then we want to move that piece out of the funnel, right? We have to move it from here up and out. So that's basically a mass moved through some distance, right? And so you can calculate the work. So you slice it up to an infinite number of slices, and that's going to be an integral, right? So I'm just trying to get you to see it's all tied into integration, right? So when you get into this engineering class or whatever it is, and the word problem's the hard part, right? Once you get to the integral, you should have what you need to do that part. Okay, that's it. That's all I'm going to say about that. If we have time at the end of this class, which we won't. I would come back and do more problems, but we won't have time. I promise we won't. All right, so we move on. Chapter 8, series. So I want to start the whole thing off here with something. There's all these different things that I could show you to kind of motivate the idea of series. I just was thinking this morning, this is the way I want to motivate it. Okay, I want us to just look at this and maybe you'll see kind of the value of where we're headed. All right. So I want us to think about the function f of x equals cosine x, right? And I want us to try and approximate this function f near the point 0 with a line. So the idea here is this. If we have the cosine function, which is in red, can you come up with a line that would be a pretty good approximation of this cosine function near 0? So near this point right here, do you all think this blue line is a pretty good approximation of the red function? No? It kind of sucks, doesn't it? I mean, the red function goes up and it curves over. This one just goes straight. I can start like tweaking the line, right? I can change the shape of the line. I don't know, maybe you think a flat line's better? Still sucks, right? Because this curves away and this curves away. But at 0, are they close? At 0, they're exactly the same, right? If I move it up here, it's not. But if I put this back where it was, right there, then yes, outside of 0, they are not the same. But at 0, they're actually exactly the same, aren't they? Okay, so let me go back to my notes. So this is really saying, you know, let's find a function g of x that's a constant. So I'm going to use k for constant. So I'm trying to, well, you know what? Let's do this. Let's do this. Let's do ax plus b. Instead of using mx plus b, I'm going to use ax plus b. So do y'all agree that this is a line? I just need to kind of figure out what a and b are. But I want it to be really close to this at 0. Yes? So we want g close to f at x equals 0. Well, okay, if I want them to be close, then can y'all tell me what f of 0 is? Well, cosine of 0 is 1, right? That's cosine of 0. That's 1. And that would mean that when I plug 0 into this function, right, I need it to be 1, sorry, into g. When I plug 0 in, this is what we want then. It's like I know the cosine function spits out 1 when I plug in 0. So the function I'm trying to come up with should also spit out 1 when I plug in 0. So when I plug in 0 into g, let's plug 0 into g. What do you get when you plug 0 into this g function? You get b is, we need b to be 1, right? We need b to be 1. If b is 1, then that would do what we need it to do. So this means that g of x would need to be a times x. And as long as I make that b a 1, then I have an approximation. I have an approximation of the cosine function, right? Where when you plug 0 into both of these, you get 1. So in our picture, that's basically this picture right here. You can pick any a you want, doesn't matter. At least they both have what's going on at 1 is the same. I mean, sorry, what's going on at 0 is the same. With me? I know this seems ridiculously dumb. Like, what's the point, right? Okay, so g of x right now is not a very good approximation of cosine. So we know they match at 0, right? The functions are equivalent at 0. They both spit out 1. What would be another kind of thing I can have them have in common? Like at 0, they both spit out 1. But is there anything else you know about the original function cosine at 0 that might be helpful?
The derivative?
Okay, the derivative. Do you know the derivative of cosine at 0? So the derivative of cosine is what? Negative sine? And at 0, what would that give you?
0.
0, right? So look at the cosine function. Isn't the slope of the tangent line there 0? So it would be nice if maybe our line had the same slope. Does that make sense? Because this line right here does not have the same slope as the tangent line to the red curve. So let me add that condition on there. See, I'm trying to get a better approximation. All right, so let me add one more thing. We know that f prime of x we said was negative sine x, right? And the derivative there at 0 would be 0. So that means we want g of x, g prime of x, to also be 0, don't we? That's what we'd like. So what's g prime? We have g, right? What's g prime? It's a. G prime of x is just a, isn't it? Because the derivative of a times x is a, and the derivative of 1 is 0. But what do we need this to be? 0. But we need that to be 0, which means a has to be what? 0. 0. A needs to be 0. Which gives me a new version of g of x. G of x now has to be 1. So you've got to make the a a 0 in order for this to work. Let me take a step back, because I understand this is confusing first time you see this. We have a function cosine, and we're looking at the value at 0. We're looking at it, and we're saying, can we come up with a line that would be pretty close to that function? We said, no, it's going to suck. But the line we have found has two things in common with that cosine function, right? There's two things in common. Here, let me put the line here. I need to make the a 0. The two things that these have in common are when you plug 0 into both of them, you get 1. And when you look at the derivative of both of them at 0, you get 0, right? With me? Okay. That's the best we can do. That's the best we can do with a line. How about we try a quadratic instead of a line? Understand? Why don't we start from scratch again, but with a quadratic? And see if we can get a quadratic to be a better approximation. All right? So I'm going to do that. I'm going to try and start with this function f of x equals cosine x. And I want to approximate it with a quadratic. G of x equals ax squared plus bx plus c. So what we're going to try and do now is figure out what does a, b, and c need to be in order to get the best approximation we can to this cosine function at x equals 0. Okay, remember, we're only looking at x equals 0. All right. Well, what should match? What's the first thing? When I plug 0 into both, I should get 1, right? So knowing this, that when we plug 0 in here, I get 1. That means over here on this one, when I plug 0 into this, I need to get 1, right? So when I plug 0 in, what do you get when you plug in 0 for x into the g function? You get c. So c must be 1. Okay, good. So I know what c has to be, right? So here's what g of x looks like now. I still don't know what a is. I still don't know what b is, but I know c must be 1. Got it? Okay, now what's the next condition we'd like to hold? The derivatives need to match, right? Well, I know the derivative of this. We just did this. The derivative of that at 0, you said was 0, right? We did that, it was negative sign. And so when we plug 0 into that, we get 0. So what that means is that over here, we need g prime of 0 to be equal to 0. Well, what's g prime of x? 2ax plus b, but we need that to be 0, right? We need that to be 0. Oh, sorry, when we plug in 0, hold on, let me put that. But we need this to be true, right? When we plug 0 in, we get 0. Right, so what does that tell me then? If I plug 0 into this derivative, what do I get? B has to be 0. Are you all following this? Okay, so tell me what the new g looks like. The new g. Ax squared plus 1, okay? So this function, g of x equals ax squared plus 1, if I graph it, it should have, when you plug in 0, it should spit out 1, and the slope of the tangent line there should be 0, right? All right, well, what's the next thing we could match? We made the function's values at 0 match. Now we made the derivatives match at 0.
The second derivative?
Second derivative. Second derivative is concavity, Cal 1, right? Concavity, concave up or down. So let's make the second derivatives match. So what is the second derivative of f? We haven't written it down. What was the second derivative of f? Negative cosine of x, right? Because derivative was negative sine x, derivative of that's negative cosine x. Now, what's the value of that at 0? -1, right? So what does that mean for us? That means when we take the second derivative of g and plug 0 in, we better get -1, right? Got it? Well, what is the second derivative of the g function? We just take the derivative of this twice, right? This is our g function. Take the first derivative, you get 2ax, and then you take derivative of that again, you get 2a. And now this means when I plug 0 into this, I should get 1. But when I plug 0 into this, nothing happens. We just get 2a. That has to be -1. Sorry, I think I said 1. This has to be -1. So that means a has to be what? -0.5, right? And that gives me now a new function. G of x equals, what is it? -1/2 x squared plus 1. Okay, that should be a function that when I graph it, when I plug in 0, I get 1. If I look at the derivative of it at 0, I should have a flat derivative. And the second derivative should also match the original function. So its concavity should be the same. Y'all want to see it? So the line, there was the line sucked, right? Let's now put in y equals -1/2 x squared plus 1. Much better, right? Near 0, they're almost the same. I've created this quadratic, right? And all I've done is made it have these conditions that the first function had, right? How could we get better? Cubic function. Why don't we go third degree polynomial? Why don't we go fourth degree polynomial? Fifth degree, sixth degree, seventh degree, right? Why don't we do something like this? Where'd you go? Why does that continually open up there? Why don't you do something like this? Well, something's running very slow. Let me close something out. Let me close this out. Wow. Close that out. Hold on, I just want to see what's eating up my resources right now. So, something's dragging. I think we're okay. All right. So here's that same idea, right? I approximated it with a line in that was the first approximation we had. And it was terrible, but it was okay, at least at that point. And then we just came up with a quadratic, didn't we? That. Now I left the line behind. That was the previous one was the dotted line. This one's better, right? That's a quadratic. It's actually this right here, 1 minus x squared over 2. That's the same as negative 1/2 x squared plus 1, right? That's what we found. Now I'm going to have the computer continue to do this for me. The next piece we'll get is that. So there is no cubic. A cubic will suck. You can't, a cubic won't work out. You have to go through the math, but I won't show it at this point. You'll find out that you'll need a 0 in front of the x cubed, okay? Let me keep going. X to the 6th. Are y'all paying attention what's happening down here? This should blow your freaking mind, okay? Look what I'm doing. I am basically creating the cosine function from the center out, right? Now look at my polynomial. It's a 20th degree polynomial, right? It's a 20th degree polynomial. But at the end of the day, it's a polynomial, right? If I asked you to integrate a polynomial, could you? If integrate it or differentiate it. If I asked you to find the antiderivative of this, term by term, right? Each one, power rule on each one, I think you'd be happy. No partial fractions, no integration by parts, no, just power rule. That's it, right? And this is a pretty good approximation, isn't it? I mean, look at it. No, out here it's not, right? But I stopped. I could keep going. In fact, hold on. I don't think I can zoom out further. That's as far as I can go, but I can tell you that if I keep going, I'll eventually cover it up. It'll mess up somewhere on the outside, but if I keep going, I'll eventually cover it up. All right.
What's the relevance of different types of functions?
What do you mean?
Why are we talking? Why do they matter?
Why?
Is it so complicated to recreate?
It's not. Why is this so complicated?
Where do the trigonometric functions come from? What are we talking?
Well, when we're taught the trig functions, right, they're usually based off the unit circle, or they're based off a right triangle. And you're taught, sine is a ratio, right? It's a ratio of two things, right? So those ratios are important because they appear all over the place. Anything that has periodic motion follows that same pattern that the sine curve does, right? Or cosine. So anything that's periodic, the trig functions are useful, right? Why would, okay, I guess my question back would be not why are we taught them? What are you suggesting we teach something different, or?
I'm just wondering what the relevance is, because they may be periodic, but they're periodic in their own different ways.
But you can always adjust them, right? You can always, if you wanted to take a sine function and adjust them so that the amplitude starts to get smaller and smaller, right? That would model something in the real world better than something. I mean, nothing in the real world really just keeps doing that, right? A lot of times,
Unique functions then.
yeah, we would just adjust them, right?
I mean, are the 6 trig functions
Unique, yes. I mean, but they're not any more unique than x squared is unique, right? I mean, they're just functions. I'm not sure I'm following your question.
I guess it's just the way they refer to it, like there's some unicorn.
The trig functions aren't a unicorn. They're just very useful. I mean, there are some functions that we just don't use, and there's some that we use all the time. And the trig functions are used a lot just because our physical world, I mean, we're always creating ratios of sides, and anytime we have things like that, we bring in the trig function because that's how we take the real world into a math problem, right? But at the end of the day, they're just functions. Okay, let me get back to this. We can sit here and talk for 2 hours. I appreciate those questions, but I want you to see something that might even be more profound than that. And that is, does anybody recognize what all the powers of this polynomial are?
Even.
They're all even. Do you remember learning in college algebra, or no, sorry, in pre-cal, do you remember learning that cosine is an even function? It is because when you do this to it, you only get even powers of x. That's what all even functions look like. So I need to take just one more step back. This thing that we just did for cosine, you can do with any function. And this representation of that function like this is called its power series. This is the power series for cosine. So all functions, right? All functions have a power series representation. And the powers within that power series will dictate whether or not it's even or odd. If all you see are even powers, it's an even function. If all you see are odd powers, it's an odd function. If you see even and odd together, it's neither, because some functions are neither even nor odd. All right. So this is huge. All right. This is huge because when you go to your calculator and you type in cosine of 4, right? Go to your calculator, type in cosine of 4. Your calculator has no idea what the cosine function is. No idea. All it knows is this. This is what your calculator does. If you type in cosine of 4 right there, your calculator will put a 4 here, a 4 here, 4 here, 4 here, and then somewhere within the code that was written by whoever programmed the calculator will say there's a predetermined place to stop. Okay. And then there is actually somewhere on your calculator where you can say, ask it to give you more digits. It's called the float, where you can get more precision. Then all it does is makes it go further out into this formula. If you don't believe me, I mean, look, what's cosine of 0? 1. Okay, plug 0 in for x here. Everything goes away except 1, right? Okay, plug in cosine of 2. All right, now that's going to suck. But you put a 2 here, 2 here, 2 here. And I guarantee you, if you get your calculator out and you just do these first few 2's in here, it'll be close to what your calculator gets if you put cosine of 2 in. Make sure you're in radian mode. That's the way computers do functions. They don't know what natural log is. They don't know what e is. They don't know what sine is or cosine. They know its power series. And that's why computer science majors have to know series, because when you're programming, you're pulling series out. You're not working with real function, like functions the way we do. Does that make sense? So the big question is, if I start with the function, how do I get to that power series? Because the method we just did, right? The method we just did is a little tedious. Okay, we're going to have to develop that method. Also, we need to know whether or not this works. This method sometimes breaks down. For example, if I, let me do a different function. Oh, here's sine. You want to see sine? Show you what sine looks like. So if we look at the power series for this, watch them start creating it. Here it goes. Look at, here's the function, and then here's the picture of it. And here we go. Line, cubic. Oh, I went too fast. 7th degree. You see what I'm doing though? Look at that. Look at that. It's beautiful. Okay, I keep going. Now, all the powers here, odd. Sine is an odd function. All right. A rational function. A rational function. Okay, this is the graph of this rational function, this part in red. The black is my approximation to it. And here I go. Dun, 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 dun. Oh, okay, so we have some issues here. Look at, I'm going. Do you see it's trying to draw it out to the right? Do you see that? Now it's taking a ton of terms to do this, but if I could keep going forever, right? Then I would eventually march out and cover this up. So these series that we're going to study are called infinite series. They go forever. Now a computer has to stop somewhere, but theoretically the series goes forever.
And so
go ahead.
These series, how are they different from like plots on a graph?
What do you, I'm not sure I understand.
Because those are like, how are they different from like coordinates on a graph where they are coordinates?
No, they are. This right here, this, everything you see here in black, this x plus 4x squared, I stopped it at 961x to the 31st power, right?
Yes.
That is a function. It's this one in black. Do you see it?
Hmm.
So if I asked you to plug a number into this blue one, it should be really close to what you get when you plug it into this. So if
Okay,
I
I
said,
see.
hey, plug 2 into this, you're going to do 2 into here. Now, I would argue that this blue function is easier to work with than the
Mhm.
black function, okay? I'd rather plug 2 into the blue one than the black one. The point here is not that we want to convert every function to its power series. The point is that every function has a power series. So you know how we've done some integrals and the compute, like even the computers had problems with it. And I told you, you know how they got the answer? They used a series. So what the computer does is it takes that complicated expression, it converts it to its power series, and then just plugs the numbers in. It's easy to integrate the power series. So you have to, this is for complicated things we can't integrate. Okay, things we can't integrate. Am I kind of making sense?
Yes.
Some of the functions that we plug into like Wolfram Alpha that
Uh-huh.
cannot be solved. or
Yeah.
can't do it. Is it because they can't convert it to a power series?
No, they can. Watch. The question here is, we've done some things on Wolfram Alpha where it says it can't do it. Okay. It's because you're asking it for the functional representation of the antiderivative. I'm trying to think. Oh, here's a classic one. One of the most classic integrals that I will ask you to compute this integral later, probably on the final exam. Oh no, I don't want to do that. I want to do this one. Let's do the antiderivative of e raised to the negative x squared. There we go. That doesn't look like that would be a hard integral, e raised to the negative x squared, but it can't be done by hand. So you get this 1/2 pi, the error function, okay? So it's having trouble. It's having trouble. But if you scroll down, God damn, I wish I had this when I was a student. There's the power series for it. It already found the power series and integrated it. So it found the power series of this, integrated the first few terms, and here it gave you the answer. There it is. There's the antiderivative of that. Now it's only gone out to the first 5 terms. You could ask it for more terms. All right. Where's it? Oh, Taylor. Well, okay. We'll get to that. There's 2 series that we'll look at. They're called Taylor series and Maclaurin series, and it's a subtle thing. It's just where we're starting. You know how when we did cosine, we started at 0, and we were doing all that thing to match it. We could have started anywhere on the cosine function. If you start at 0, it's called the Maclaurin series. If you start anywhere else, it's called the Taylor series. Now, Mathematica, they call everything a Taylor series, because a Maclaurin is when you start at 0, a Taylor is anywhere else, but a Taylor at 0 is Maclaurin. So it's kind of like a box. A box is a rectangle, but not every rectangle is a box. This is a Taylor series centered at 0, so you can call it a Maclaurin series. I thought I saw a question. No. So this is, I mean, this is crazy what's out there now, right? I mean, like literally, you cannot do this by hand, but if you use a power series, you can do it. Now, why is that important? If I do that now, and I put some limits of integration on it, right? So let's say I go from 0 to 1 of e raised to the negative x squared dx, the computer will have absolutely no problem doing this, because it's just done its power series. It's done the power series. Remember the answer we had just a second ago that I pointed at? It just took the 2 limits of integration, plugged them in, subtracted. That's all it did, and it found an answer. Here it is. And see, if I say more digits, see that? I clicked that button. It now just went and did more of the power series, okay? And then plugged in 0 and 1 and got the answer, and now I've got more digits. You want more? We'll get more. There you go. Okay, more of the power series, right? Power series are basically the foundation of all numerical computations that we see on websites and stuff. So pretty powerful stuff. I believe, let me try one thing. I was talking to the people at Wolfram the other day because I was having an issue. If I put n integrate e raised to the negative x squared. Okay, if I do that, comma x, if I tell it to do this, I know it's hard to see, but I put n integrate instead. I'm going to see what it does. Didn't like it. Let me try this. Whoa. All right, we'll do something else. Let me get off their website. Let me just go to Wolfram Mathematica, their program. This is the program I use when I'm presenting all this stuff that I put together. So this is, I'm going to put integrate exponential of negative x squared, comma x, should get the error function, okay? But if I change this to n integrate, that means numerical. That means it can use series. I should, oh, okay. So it doesn't give me, see, it's still not going to give me the power series. So that's okay. So here, we'll do this, watch. How about I do series. I haven't done this in a long time, so I don't know if my notation, my syntax is right here. No. I'm sorry. It's easy for me to go off topic here. There we go. Okay, so this gave me the series expansion of this, and it gave me the first three terms, or first two. So here's what I can do. This is really actually cool. I can do manipulate. So what I'm going to do is create a slider real quick. I'm going to say m, comma 1, comma 100, comma 1. So what I've done is I forgot to put them here. There we go. So here we go. I've created a slider that'll start generating a series for me. It'll go out the first 100 terms. There you go. There's the first 100 terms of that series, of that power series. Maybe if I put 2.0, I think it will do actual numbers in front of those. Oh, why is it not doing that? Okay, I'm going way too off topic. I'm sorry. Okay, we have to stop. All right, so I hope that if anything, this first little intro to chapter 8 is just to show you that, look, big picture, this is what we use, all right? It's okay that your integration by parts is terrible, or, you know, I mean, you still need it, but I'm just saying, like, in the real world, we numerically solve things for the most part. All right, let's get to it. So we have to learn how to crawl before we walk. So the very first topic here in this section is sequences, not series, sequences. So 8.1. So I want you to just consider something you've looked at before in your life, and that is take this function f of x equals x squared. All right. So you know everything we just did, trying to get this cosine to become just back burner, back burner. Okay, this is brand new. We're just clear your minds. We've got this function f of x is x squared. We all know what it looks like, right? We all can graph this. If I draw the graph, it's going to look like this little parabola. If I start plugging values in, right? If I plug in 0, I get 0, 1, I get 1, 2, I get 4. I could plug in 1/2. I could plug in any number I want, right? So the domain of this function is all real numbers, right? So the way we could kind of represent what's happening here is this function takes a real number. I'm using a double struct capital R to represent all real numbers. This function, colon, takes real numbers in and spits out real numbers, right? Real number in, real number out. Pretty much every function you've dealt with in your life has been like this. You plug in a real number, it spits out a real number. Yeah? What I would like for you to consider now is something a little different. I'd like for you to consider a function, f of n. So I'm going to use n instead of x. And I still want it to do the same thing. I want it to square what you put in. All right? But here's the condition. What makes it different than the one above? You know how this function took a real number in and spit a real number out? This one, I want this function f to not take real numbers in, but to take these in. Double struct capital N. Do you all know what double struct capital N represents? No?
Natural?
Natural numbers. This is the natural numbers. The natural numbers are just the numbers 1, 2, 3, 4, and forever. Okay? This function, I'm telling you, I want it to only go from n into r. So it only takes natural numbers in and it spits real numbers out. All right? What would the graph of this look like? Would it be a parabola? It'd be a bunch of points, right? Can you plug 0 in? No. Can you plug in a half? No. Can you plug in 1? Yes. So I can plug in 1 and it will spit out 1, won't it? I can plug in 2 and it'll spit out 2, not 2, sorry. 2 squared is 4, right? I plug in 3, it'll spit out 9. So instead of looking like a nice, solid, continuous graph, it's just going to look like a scatter plot of points, isn't it? It's going to be more points. They're all, now they will all lie on this parabola that doesn't exist, right? But they would all coincide with points on the real parabola, wouldn't they? So all those dots would appear on this parabola somewhere, but they are not the same thing, right? The one in red, this one that we've studied, or here, the one in yellow here, this is what we've been studying, right? Functions, nice. We talked about continuity in Cal 1. Can you draw it without picking up your pencil? And now I'm asking you to consider this new function. And the main difference, the only difference, is I've made a domain restriction, right? I've restricted the domain. I've said you can't plug in anything you want. You can only plug in these numbers, 1, 2, 3, 4, 5, okay? This is what a sequence is. A sequence is a function that goes from the natural numbers into the real numbers. That's it. That's what a sequence is. All right, so a sequence is a function from the natural numbers into the real numbers. Now, the thing that we do is we start to mess with the notation, all right? We start to mess with the notation a little bit just to make our lives a little easier. So you know how I wrote here a second ago, f of n equals n squared? That's the way I started this example. I'd like to change the notation because f of n might confuse you and you might forget that this is a restriction of the domain. The only thing that really tells you that is I'm using n instead of x, right? But there's nothing really, other than that, there's nothing that tells you that this is a sequence. So what we do is we change the notation and we stop using this. And what we do instead is we write a subscript n equals n squared. That's the notation we use for sequences, a sub n. Now, keep in mind, this is a specific example of a sequence, right? A sub n here is n squared. I could define a different sequence if I wanted to. Let me do that. Let me put another sequence over here next to it. How about a different sequence? A sub n equals, I don't know, 1 over n plus 1. There we go. I just created that. I just made that up out of nowhere. See, there's two different sequences here, right? What's kind of nice about this notation is that if I write this down, a subscript 1, then that means you plug 1 into this, right? That means you just square the 1. 1 squared, and that is 1. And then a sub 2 would be 2 squared, which is going to be 4, right? A sub 3 would be 9, and so on and so forth, right? So when we think about a sequence, right? Think about all sequences, right? Don't they all have the same inputs? 1, 2, 3, 4, 5, 6, 7, 8, right? They all have the same input. The only thing that distinguishes one sequence from another is the output, right? The output's what's different. So what I'd like to do here is I'd like to write this sequence. I'd like to write this sequence by just looking at its outputs. Okay, so what are the outputs of this sequence? The numbers are what? 1, 4, 9. Next one would be 16. I'm going to write those down in a list. And when I do a list, I'm going to start with a set of braces, and I'm going to do 1, 4, 9, 16, dot, 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 and then close the brace. This is a representation of that sequence. Now, you have to do a little kind of, there's some assumptions here, like 1, 4, 9, 16. We see a pattern, don't we? We see a pattern. I think we could all look at that, hopefully, and conclude that, yes, the next number in here is 100, right? No, I was trying to trick you. 25, right? 25, then, right? So do we all agree? If I gave you this, in other words, if I gave you this, could you tell me it was n squared? Yeah? Yes? If I gave you that, could you say, oh, that's the sequence n squared? This one might be harder. Let's list out the first few of these. A sub 1 would be 1 over 1 plus 1, that's a half, right? A sub 2 would be a third. A sub 3 would be 1/4, and keep on going, right? 1/5, 1/6, 1/7. So this sequence written out as a list would be a half, a third, a fourth, a fifth. I think that's good enough to see the pattern. The question becomes now, could you go from this back to this? If I gave you this, could you go back to that? That's the hard, this is where things start getting hard. And as long as I've been teaching this, this is the part where it's very hard to teach this. Students either see it or they don't. And it's a very difficult thing. So we're going to do more examples of this, but I want to make sure we get the notation, everything down right before we move on to specific examples. So in general, okay. In general, A sub n, some sequence, is just a list of numbers, right? That's all it is, a list of numbers. It's the first number, A sub 1, followed by A sub 2, followed by A sub 3, followed by A sub 4, comma, dot, dot, dot. And that sequence goes forever, doesn't it? That sequence of numbers goes forever. This is called an infinite sequence. And these are the ones we're going to be most interested in. This is an infinite sequence. Now, if I don't want my sequence to go forever, there is a way that I can tell you to stop. So I can do this. If I write a sub n less than or equal to 10, then that means your list will start where? At 1, and then you will stop when you get to 10, right? And this would be an example of a finite sequence. But see, I have to tell you to stop, don't I? I have to tell you to stop somehow. If I don't tell you to stop, you assume that it goes forever. I could do something like this. A sub n bigger than 3, less than or equal to 7. What would that list be? Careful. A sub 4, a sub 5, a sub 6. Do I include a sub 7? A sub 7. I kind of mess with these inequalities on purpose. Your n must be bigger than 3, right? Not bigger than or equal to. So that means I have to start at 4 and then stop at 7. Everything less than or equal to 7. Is this making sense? We're just trying to make sure we understand like the notation ideas here. Now, for each of these 3 that I've given you, for each of the 3 I've given you, there's another notation for each of those, all right? I'm going to show you the other notation. I'm going to put it on the side, and I'll do it in black, but I'll make it kind of bolded. For this on the side here, for each one of these 3 cases we have, another way you could have written these, this first one, you could have written a sub n within a set of braces. Now, I know that that doesn't really seem like we've done anything here, but what you can do is on the bottom, you put n equals 1, and up here you put infinity. If you write a sub n with n equals 1 to infinity in braces like this, this basically means you start at 1 and go forever. Now, we normally don't write this notation, it's understood. So you just write a sub n, that's like the default. The default is that right there. It goes forever. But how could I write this next one using that same idea? Brace a sub n. What do I do? N equals 1 to 10, right? And then this one. N equals 4 to 7. All right. We're almost ready to get into some fun stuff. All right. If I wanted to use a different letter other than N, I would use something, I would not use X or Y or Z, because then that would confuse you with functions that we've been doing. The standard letters we use for sequences are N and K. You'll also see J, sometimes L, okay? But for this class, mostly N and K. So everything I've done here, if I just replace this with K, that with K, then that would be kind of within the standards for sequences. All right. So now we get to have fun. I get to see what you can figure out. Now I'm going to ask you to come up with, I'm going to go around the room. So you might get put on the spot and you might not be able to get it. And I don't want you to feel bad. Okay. But I just always have enjoyed doing it like this. All right. Okay, here we go. I'm going to write the sequence as a list. You have to give me the formula. It's going to start with the easy ones. All right, so how about this? So I would like the formula for this. A sub n equals what? So I'll take volunteers first. What formula would spit out? Go ahead. Just n. That's it, right? This is almost like the identity function, right? You plug in 1, it spits out 1. You plug in 2, it spits out 2. You plug in 3, it spits out 3. Do y'all see that? All right, that's kind of boring one, right? But it's a standard one, right? Okay, how about this? What is it? N minus 4. What do y'all think? N minus 4. N minus 4. A sub n equals n minus 4. So if you don't see this, here's one way to think about it. You can do this like either above or below each of the numbers. Think about what the input is for each of these. 1, 2, 3, 4, right? So you're plugging in 1, it's spitting out -3. You're plugging in 2, it's spitting out -2. You're plugging in 3, spitting out -1. Plugging in 4, it's spitting out 0. And each one of these keeps going up by 1, right? So if it keeps going up by 1, then it's linear, right? It's linear. And to turn 1 into -3, you have to take 4 away. To take 2 to -2, you have to take 4 away. So this grows the same way this one does. So it looks like it should be an n, but we have to shift it. It's almost like we're taking everything in that first list, right? And subtracting 4. Everything here, subtract 4. So take that, subtract 4. Done. Works. So far, okay? Two, 4, 6, 8. You want that one, Christian? It's just 2n. 2n. You're just doubling the input, right? 2 times 1, 2. 4, 2 times 2, 4. 2 times 3, 2 times 4. All right. Question?
Series, was that right?
No, Maclaurin? No, remember I said dump all that. Way back burner on that. These are sequences. Okay, we haven't, series are a completely different animal. So a sequence is a sum of, a series is a sum of a sequence. It's you take all these numbers and add them up. That's a series. We're not talking series yet. And then you have series, then you have power series, which are different. Then you have variables involved. All of these are just a list of numbers. Okay, so the next one is -5, -3, -1, 1, ... Okay, you know what? Hold on. I think I'm pushing too far with that one. Let's do this. Let's hold off on that one. That'll be the next one. Let's do this. 1, 3, 5, 7, 9. By the way, the one we just did right here, wasn't this the even numbers? This sequence right here, 2n, creates a list of the even numbers. This is all the odds, right? So what would generate the odds? 2n take away 1. The odds are basically all of these numbers, but just subtract 1 from each one, right? So 2n minus 1 for this one. So who wants this next list here? What do these all have in common? They're all odd, right? The way I like to look at it is this. How much does this go up by each time? We're adding 2 each time, just like this, added 2 each time, right? This one added 2 each time. If I add 2 each time, then I'm going to need a 2n in there, because that will help me add 2 each time I move. So I'm going to need a 2n. But where do I want to start? at -5. So when I plug in 1 into this, I need to get a -5. So what should I subtract from this? 7. Take away 7. Now, if you plug in 1, you get 2n minus 7, that's -5. Plug in 2, you get 2 times 2, it's 4. Take away 7, you get 3. Understand? You could do that the same way here. How much did these jump by each time? 1, right? So I needed a 1n, not a 2n, a 1n, and then I can just figure out where I want to start. Same sort of idea. Did I skip a page there? No. All right, I'll go off my notes. This is what I have here, so. Oh, okay. Right into the fire here. Anybody at home? Let me give you a hint. Look at every one of these numbers as fractions and think about what the numerator and denominators are. Look at them separately. Like, could you create a formula to generate what's going on in the numerators? Could you create a formula that's generating what's going on in the denominators? Can y'all tell what's happening in the numerators? If you were to list out the numerators, what would they be? Right? -2, 0, 2, 4, maybe 6. How much are they going up by each time? 2, right? So I know I'll need a 2n up top. But where am I starting? -2. So if I plug in 1 here, I'm going to get 2. I need it to be a -2. So what should I do here? Take away 4. That's the tops. That should generate the tops, right? -2, then a 0, then 2, then 4. With me? Over. Now, what do the bottoms look like they are? 5 could be anything because the top is 0. 9, 11. So maybe 5, 7, 9, 11. 5, 7, 9, 11. So those go up by 2 each time. So 2n, but I need to start where? At 5, so I need to plus 3. There you go. Like when I started this, I said, this is a point in the class where I get students that like get it. And then there's students who are like, whoa. So, you know, ask questions. If you feel like lost, you need to let me know. These won't get easier. Ready for the next one? This is one of the most important ones that we will look at. -1, 1, -1, 1, -1, 1. What is that? Negative cosine.
No, I just saw the 1.
Yeah. You actually might be able to do this with a cosine. I should mention this. When you have a sequence of numbers, the formula that generates it does not have to be unique. In other words, someone else may come up with the formula that generates the same sequence and your formulas don't look the same. It is possible. There is a way we could do this with cosines, although you don't have to work that hard to get this one.
-1 to
tricky.
the n.
-1 to the n. Good. Let's see. Does this work? -1 raised to the n power. Well, we plug in 1 first, right? What's -1 to the first? -1. Okay. -1 squared. 1. -1 cubed, -1. -1 to the 4th, 1, right? So it is going to alternate, right? It's going to alternate negative, positive, right? Yes. Cosine what? Cosine of n minus sine of n. No, because if you start plugging in values like cosine of 1 minus sine of 1, sine of 1 and cosine of 1 are not nice things. You would have to put something with like an n pi inside the cosine. Right? Let me see. Maybe I've never done it with cosine. Let me try it. I would have to have, well, what is cosine? Cosine is 1 here, -1 here. So those are multiples of pi. So I would need something like this. Pi n. Let's try it. If I plug in 1 for n, what do I get? I get pi. Cosine of pi is -1. Now I plug in 2 for n. What's cosine of 2 pi? 1, right? And then I plug in 3, cosine of 3 pi. -1. So that would work. But you need pi n inside cosine. Could you do it with the sine? Because sine is positive here and here. Or sorry, 1 here, right? And -1 here for sine. So I would have to do something like sine of pi over 2 plus pi n. But you know what? I need to start at negative pi over 2. So if I plug, no, hold on. Sorry. I think I was right first time. I was right the first time. Okay. Because we want to start at -1. If I plug in 1, right, for n, that means you go pi over 2. Pi over 2 is straight up, right? Add pi to it. Now you're down here and sine of that's -1. And then when you plug in 2, it's going to come another pi. Yeah, that'll work also. Now, I don't recommend we use the trig, okay? Because at the end of the day, we're going to do series later. And the whole idea is to turn cosine into a series. So we don't want to have cosines and sines within there. So it works, it's good, but I'm not going to mess with it. This is so much more clean, right? -1 to the n, boom, done. How about this? 1 -1, 1 -1. 1 -1. Same sequence, but starting with positive. What can you do?
The negative of the last one.
Just, oh yeah, just take the last sequence and multiply everything by -1s, right? So just put a negative in front of this. That would work. Negative in front of that would work. Because it takes all of those and just changes the signs. But hold on, isn't that the same as -1 times -1 to the n? Isn't that the same thing? And don't these have the same base? And the exponents on those are a 1 and an n. So you can put them together, can't you? And you get -1 to the what? -1 to the n plus 1. That would also work. Think about what would happen. If you plug in 1 now, what happens? Plug in 1, you actually get 2. So you get -1 squared, and that's this first one. Now, if you plug in 2, you get 3 up here, and that'll be an odd power, so you get negative. In fact, when you really think about it, couldn't I do -1 to the n plus any odd number? Think about it. If I put any odd number here, then when I plug in 1, 1 plus an odd is going to be even. And then when I plug in 2, 2 plus an odd will be odd. So that should create the same thing. You could make the same argument for this one if you do what? Add any what? Add any even to it. It would be the same. Both of these sequences are your first examples of what are called alternating sequences. Because they switch signs. If I take you back to that graph I had earlier of that cosine in here, or where was it? This cosine, when we did its power series. Do y'all see that when we look at these terms of the polynomial here, that it goes positive, negative, positive, negative, positive, negative, positive, negative? This is an alternating series. We're talking about sequences right now, but we are learning how you can, this negative one to the n, we are learning how you can make things flip signs, all right? It'll be useful later. It'll be useful throughout the rest of this, pretty much the rest of the class. All right, I'm gonna put a couple up for you to try, okay? You ready? Hold on, I got to think through this one a little bit. Give me a moment. I believe that's right. Let's try and come up with those. Yeah, I'll be right back. I'm asking. You all getting anywhere or no? First one? I hope I did the second one right. Alternates. Okay, we'll look at the second one. How about the first one? Yeah, tell me what you got. -1 to the n, 2n minus 5 in parentheses. Okay. N plus 1 squared. What do y'all think? Wait, hold on, what? -2 to the n plus 1. Oh man, I just see that I made a mistake. Shit. Do y'all see my mistake? No, well, this right here needs to be something else. Oh, shit.
The 2 needs to be a 1, I think. So
2
it can be
needs
like
1.
yeah,
2
so-
squared? No, hold on. What are these down here? 5 squared? No? Are they going up by ones? Hold on. What was I doing? What in the world was I doing? Okay. Look, the top, look at the top. 3, 5, 7, 9, right? Odds starting. Yeah, let me redo this. I apologize. Let's see if the second one's right. I think I did the second one right. All right. I just made this up out of my head, so this is my fault. Does anyone have anything on the second one? Take this to the other side. I'm sorry, my first example should be something that works, right? What made you think though? All right, let's see. I'm going to try and just looking at these right here, right? Just those right there. Do we agree that the bottom looks like 3 squared and then below that 3 cubed and then the one next to it 3 to the 4th? Do we agree with that for those 3?
Yeah.
Yes. Now don't worry about the signs because it's a positive number, negative number, positive number, negative number, positive number, negative. I can handle that with the -1 to the n thing, okay? Just looking at the numbers themselves. Now on the top, I have 8, 10, 12. Those look like even numbers, right? So let's see, if I go backwards, what should the next one be if I follow this pattern? What's on top? 6, what's on the bottom? 3 to the 1, is that 2? Yes. Go back again. What would this be? 4. I'm not looking at the negative because remember, I can take care of the negative with the -1 to the n. I have a 4 following this pattern. Don't look up here yet. Following this pattern. 6 will go back to 4 and the bottom we get what? 3 to the 0, right? Which is 1. That works, right? And then if I go back again, this on top would have to be a 2. And then what would this one have to be? 3 to the -1, but 3 to the -1 would come up as a 3 and become a 6 with the 2. So the harder one I did right. I don't know why I messed up the easier one. Okay. So this is it. Do you see this pattern? So let me create this. First, I needed to alternate starting with positive. To do that, I put -1 to the n or n plus 1? Plus 1. Okay, do you see just by me putting that, I've taken care of the plus minus, plus minus, plus minus. I don't have to worry about anything else. Now I'm going to look at I'm going to multiply that times the fraction. And let me take care of the numerator first. All the numerators are just 2, 4, 6, 8, 10. That's just even numbers. I create that with 2n, right? Okay, the bottom, these are all powers of 3, right? Powers of 3. So it's 3 raised to these powers, but my powers go up by 1, -1, 0, 1, 2, 3, but they start where? -1. So I need to put here n minus 2. There. That makes sense how I did that? Now, what the hell was I trying to do on the first one? I missed the 9 on the bottom. Let me see. I don't think that's what I was intending. Hold on. Let me see. Yeah, I think it's really jacked up. Okay, let's talk about, it's alternating, right? It's alternating, negative, positive, negative, positive. I take care of that with -1 to just the end. That'll take care of the negative, positive, negative, positive. The numerators are all odd numbers starting with 3. 2n plus 1. Okay. The denominators were all supposed to be, I think in my mind, I was thinking that they were all things that were squared. So I think I was thinking this should have been what, 5 squared? This should have been 4 squared. This should have been 3 squared, and this one should have been 2 squared. I think that's what I was thinking. But I also could have been thinking powers of 2. 2 to the first, 2 squared, 2 cubed, but that should have been an 8. It's all, you know what I'm saying? So I'm sorry about that. This should be a 9, and if that's a 9, make this one a 4. Now it's doable. Don't worry, I'll get lashes in math hell when I get there. I'll get lashes for that.
Nice to see that you reinvent this course every year.
Yes.
How many years is that?
This is the first year. I don't know, 20. All right, so what would that be on the bottom? 2 to the, yeah, we want to start at 2. Sorry, not 2. Sorry, they're not powers of 2. They are all squared, but what's the thing being squared? N plus 1. Yeah, that's what the part, yeah. My formula was wrong. Okay, so I have a fun project for everyone, okay? I want everyone next class to come with 2 that you've created, okay? You create the list yourself, all right? Don't go freaking crazy, okay? Because I want your classmates to be able to get them, all right? Make it just a pattern that's within reason. Don't do anything nuts, all right? Like the one that I did here that actually worked, I like something like this because looking at the first few numbers, you can't tell anything. It's these 3 that give you everything right here. From these 3, I had to build backwards, all right? So I'd like for you to just create 2 sequences and turn those in on one page. And your other page, I want you to put the formula, all right? So you get to make them up though, all right? And then what we'll do is I'll put them all together, I'll compile them into a document and I'll send them out to everyone and everyone can mess with them, all right? So you kind of play with those yourself. Just, oh yeah, you want to do what I did and just do something that doesn't work? Yeah, go ahead and do that. Come on, y'all got to cut me some slack. All right, I'm still human. All right, moving on, okay? We need to talk about something that maybe you have seen. I know some of you have, some of you haven't. Have you ever seen this before? N factorial, okay? So that's this symbol, that exclamation point is a mathematical symbol. This is called N factorial. And all it is just a very, very convenient way to write something out that's really long in a condensed form. So I think the best way to see it is just do an example. If you write 6 with an exclamation mark next to it, it means you take 6, multiply by 5, then multiply by 4, then multiply by 3, then multiply by 2. You don't have to multiply by 1, but I like to put it there. Then you multiply by 1, and that is what 6 factorial is. So if you get on a calculator and do 6 times 5 times 4 times 3 times 2 times 1, that's 6 factorial, all right? This comes up a lot in statistics, probability and statistics. One way I could explain to you a real quick factorial is if I took everyone in this room, okay, and right now there's 1, 2, 3, 4, 5, 6, 7, 8, there's 9 students in the room. if I were going to line you up against the wall, okay, just put you all up and say, hey, line up against the wall. How many different ways could that happen? 9 factorial. Why? Because there are 9, 1, 2, 3, 4, 5, 6, 7, 8. There's 9 slots that we can line up in, right? So we have to pick that first person. So that first person can be any of the 9 of you, right? 9 of you. And now the next person goes in, and that could be any of the remaining 8. And then the remaining 6, 7. Geez, man, what's going on? 5, 4, 3, 2, 1, right? So that's how many different ways we could do it. 9 in the first slot, 8 in the second. If you multiply all those together, that's how many different ways we could do it. All right, so, you know, what's the probability that you're the second person in line, right? It's 1 out of however many possible ways, you know what I'm saying? So probability comes into play quite a bit. So that's 6 factorial. An interesting curiosity here with factorial is that factorial is not defined for negative numbers, right? That would make sense with this definition, but 0 factorial is defined, and it's actually defined to be 1. You would think 0 factorial is 0, but 0 factorial by definition is 1. And I know that that bothers students, but there's a nice mathematical explanation to this. The factorial is actually another function. It's not, yes, it is this function, but right now, if I were to say, you know, what's 1/2 factorial? That wouldn't make sense to us. Factorials are only defined here in this class for natural numbers. Well, 0 also. 0, 1, 2, 3, 4, factorial, all those you can do. But there is another function that will handle the negatives and the fractions also. It's just beyond the scope of this class. So 0 factorial is well defined to be 1. All right. Now, when you write n factorial, what it means is you're going to take n, multiply that times n minus 1, then multiply that by n minus 2, and you're going to keep doing that until you get down to 1. All right, that's the idea here. Each time you do a multiplication, each number is 1 less than the one before it. So with that idea, I'd like for us to find what n plus 1 factorial over n factorial is. So let's start with the top one. N plus 1 factorial means I start with what, and then multiply what, and then multiply what, and then multiply what? You tell me. So if you do n factorial, you start with n, right? So if I do n plus 1 factorial, I start with n plus 1. Okay, now I'm going to multiply that by 1 less than that. So yeah, 1 less than n plus 1 would be n, right? And then 1 less than that would be n minus 1, and 1 less than that would be n minus 2. And I keep going, right? Keep going, dot, 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 and I stop when I finally get to 1, right? That's all divided by n factorial on the bottom, which is same thing, except start with n. n minus 1, n minus 2, dot, 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 all the way till I get to 1. Y'all okay with that? And do you see all the stuff that cancels? What's that? Except for the n plus 1, right? Everything else goes away. So what I want you to see with this is that everything here, right, is really what? Which is just n factorial, right? This is just n factorial, and this right here is also n factorial, and so the n factorials cancel, and you're left with just the n plus 1 up front. So if you have n plus 1 factorial over n factorial, your answer should be n plus 1. Let's see if you really understand that. try this one. Find 2n plus 2 factorial over 2n minus 1 factorial. Let's start with the top one. By definition, the top one is what first? 2n plus 2. The next thing I multiply by is one less than that, right? Which is 2n plus 1. And what's the one after that? Just 2n. What's the one after that? 2n minus 1. What's the one after that? 2n minus 2. But wait a minute. I'm going to keep doing that till I get down to 1, right? Do you all see that everything from 2n minus 1 down, do you all see that all of that together is really just the bottom, right? This is 2n minus 1 factorial. That's what this red part is. And so it will cancel with the bottom. So I'm not going to write out the bottom. I'm just going to leave the bottom as 2n minus 1 factorial and then cancel all that out. And I'll be left with 2n plus 2 times 2n plus 1 times 2n. All right, this is actually a really good place to stop. We're still in this section 8.1. We'll spend probably most of next class in 8.1. I spend a lot of time in 8.1 because you need 8.1 to do anything else after this. And if you struggle with 8.1, then there's some issues. So I would say do that homework assignment where you create your own little things. And then on page 434, numbers 5 through 8. Those are, they give you sequences and they ask you for formulas. All right. That's it. Y'all have a great weekend, right? Yes. Let's see, section, export section. What's that? Till it goes to 1. When you multiply, you know how like 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, right? You would keep on doing whatever this is. You see, we don't know what this is. This is a number. We don't know what it is. So we're saying, okay, we're going to take that number, multiply it by 1 less than that, 1 less than that. But we have to stop when we get to 1. Like we don't know when it happens. Eventually it will, right? Because no matter what you plug in here for n, if you plug in 100, right? You plug in 100, then this would be 202. So it'd be 202 times 201 times 200 times 199. So eventually it goes down to 1. We don't know how many terms there are because we don't know what n is. That makes sense? Okay. Yeah, keep it arithmetic. Keep it like, I would say, linear stuff like 2n something or 3n, or you can, that would be a good one. You know how I was jumping by 2 each time, maybe jump by 5 or jump by, and then powers, 2 to powers, 3 to powers, squareds, cubes, things like that. Any questions?
Just asking about like, what was the function you were talking about for the factorials?
Oh, you want to know what that function is?
Yeah.
Yes. Hold on. I'm going to bring it up because it's cool to look at it. Give me a second here. hold on just a second. I have a student here with a question, so y'all just hang tight.
Sure.
All right, hang tight. Okay, you there?
Yeah.
Okay, so you may have heard of this before. It's called the gamma function. I'm trying to find a good link to it here. Gamma function. All I can find is Wikipedia stuff. Oh, Wolfram, maybe Wolfram has. Hmm. So here it is. Here's the gamma function right here. The gamma function is actually defined to be an improper integral. So I would suggest you look at this if you're interested in knowing about it.
Yeah.
But with this gamma function, it is defined for all positive integers, but it's also defined for negative numbers and fractions and stuff. It does have problems where it's undefined, but this is a graph of the gamma.
Yeah. It looks weird.
Yeah, so like if you do like 1 factorial would be 1. Actually, it's gamma of n minus is n minus 1 factorial. So it's a little weird. When you plug in 2, that's really 1 factorial. When you plug in 3, that's really 2 factorial. When you plug in 4, it's really 3 factorial. So
Yeah.
it's shifted over by 1, but it's a cool function, and you can see that when you plug in 0 into the factorial, you'll get 1. It actually corresponds to this point right here. You plug 1 into the gamma function, it spits out 1, which is why 0 factorial is defined to be 0 factorial is defined to be 1.
Yeah.
So it's pretty cool. You can look into it. Gamma function.
Yeah. Sure. Thank you.
Okay. Have a good one.
You too.